Okay, now this little angle down here, let's call this angle theta 1. And I want to verify formula 4 for you. And it really is just trigonometry combined with what we learned in with the dot product back in the previous chapter. So can you take the cosine of theta 1 for me and tell me what it is? So just think in terms of lengths of sides of a triangle here. So you're going to have to take some magnitudes to make this work. So take the cosine of theta 1. So focus on, I'll erase this in a second, but focus on this guy that I'm encircling as a triangle, right? And what do you know from SOHCAHTOA? What do you know about the cosine? It's the CAH part of SOHCAHTOA. Cosine is equal to adjacent, the length of the adjacent over the length of the hypotenuse. So you have to think in terms of magnitude here. So what would the length of the adjacent side be? Right, but that's just a sub t. So adjacent side, we'll call its directed length at least a sub t. Why? Oh, because t is a unit vector. When you take its magnitude, you get 1. It doesn't contribute anything. Divided by, what's the length of the vector in blue? Well, magnitude of a, because that's a vector, right? Now, when you solve for a sub t, what do you get? Magnitude a, leave a little space, times cosine theta 1. Yeah? Can't you just throw in a magnitude of t? Because it has length 1. Everybody buy that? Let me make that a little bit bigger. It's hard to see. So that's supposed to be magnitude a times magnitude t times cosine of theta. Isn't that another name for a dot t? Yeah, so that's it. That's all there is to it. If you call this guy, say, theta 2, and put a copy of the black vector here, you also can add the black vector a sub tt and the green vector a sub nn and get the blue vector a, and do a very similar proof using trigonometry and definition of dot product, the alternative definition of dot product involving the cosine, to show that a sub n is equal to a dot n, the acceleration vector dotted with the principal unit normal vector. Any questions on those? Okay, and then number 6 is what I've been talking about that I haven't proved yet. N points in the direction that the curve is bending. In other words, the question is, why does n point in the same direction as the vector in green right here? Why not the other direction? Well, okay, let's go back up here and let's look at what a sub n equals. ds dt squared, the speed squared, times the curvature, right? Is the speed squared ever going to be negative? Nope. Is k, curvature, ever going to be negative? No, just think about the formula for it, magnitude of t prime divided by magnitude of r prime. Got to be positive. We're assuming non-zero vectors here, too. So a sub n, if you look at this, it's going to, assuming that there is some bend in the curve, a sub n is going to be bigger than 0. Would you agree with that? So it's not going to be negative in particular. Well, that's why n has to point in the same direction as the vector in green, in the direction that the curve is bending. In other words, a dot n is a sub n. It's got to be bigger than, assuming there is bend in the curve, it's got to be strictly bigger than 0. What do we know about the angle that, so remember another name for a dot n is magnitude a, magnitude n, cosine, what we call theta 2 in this case. What do we know about theta 2 if the magnitude a, magnitude n, cosine theta 2 is positive? In other words, if a dot n is positive. The angle between the two vectors, a and n, which is the same as the angle between a sub n and a, it has to be acute if the dot product is positive, right? And if n pointed in this direction, that theta 2 be obtuse. Do you see it? So that's why it has to point. That's at least analytically why. There's other intuitive reasons why we would want it to point in the direction the curve is bending, but analytically that's why it works. Now, you might think you need to compute a sub n by taking a dot n, right? But in practice, you want to avoid finding n usually because the derivatives get a little complicated to compute. Let's go back up to that picture. Let me zoom in because it's kind of messy. So just consider this triangle, right? Consider let me draw it separately. I'll color code it so everything looks the same, but I'll just draw it as a triangle. So green is a sub n lengthwise, right? Because n is the unit normal vector. So lengthwise, this vector in green right here has length just a sub n. Does everybody agree with that? You take the magnitude of it, and since n is the unit normal vector, you can pull out that scalar of just a sub n. So the length of that vector in green is a sub n, but I'm drawing this actually I'm drawing that the length of that vector. I'm not drawing the arrow. And then this side, a sub t, but that just has length a sub t. And then this guy, the length of your acceleration vector is the magnitude of a. Okay? What are we looking for? We're looking for, can't we use the Pythagorean theorem on this thing? You bet. So the Pythagorean theorem says that a sub n is going to equal what? Well, I bet it's a square root. Going out on a limb there, right? So the square root of, let's see, if you write it in terms of the Pythagorean theorem with everything squared, it's going to be a sub t squared plus a sub n squared equals magnitude of a squared, right? But if you solve it for a sub n, won't you get the square root of, it's got to be the magnitude of a squared, and then minus a sub t squared? Yeah? Pythagorean theorem? Everybody believe that? If you don't, just write down a sub t squared plus a sub n squared equals magnitude a squared. Solve for a sub n. So let's add that to the list then. And this turns out to be the handier formula. Square root magnitude acceleration vector squared, that's the hypotenuse, minus a sub t squared. And you can, especially if you have a sub t, isn't that a really convenient formula? And you have a,